Welcome to the world of MIPS Assembly Language. The full form of MIPS is Microprocessor without Interlocked Pipeline Stages. Introduction to your journey. Hello, aspiring learners. I'm Krishna Kumar Singh, and I am thrilled to embark on this educational journey with you through the fascinating realm of MIPS Assembly Language, and in short MIPS. As we delve into the intricacies of this programming language, we'll uncover its nuances, explore its functionalities, and unravel its potential to empower you in the world of computer science. In this inaugural video lecture, we'll lay the groundwork for our exploration. We'll discuss what MIPS assembly language is, why it's relevant in today's technological landscape, and how it can serve as a powerful tool for understanding computer architecture and programming principles. Whether you're a novice eager to grasp the fundamentals or a seasoned enthusiast seeking to deepen your understanding, this series aims to cater to learners of all levels. So, buckle up, and get ready to embark on an enlightening journey into the world of MIPS assembly language. Without further ado, let's dive into our first lecture and set the stage for an enriching learning experience ahead. Okay. In this lecture, I want to start the MIPS assembly language. Different computer have different instruction sets. In this course, we are focusing on a specific type of the processor, and we learn its assembly language, MIPS processor, and their MIPS assembly language. Early computers had very simple instruction set. It's because they want to simplify the implementation of the control unit and the data part of the processor. Even now, some of the modern computers also have simple instruction set. So we have two types of the instruction set: RISC reduced instruction set computer, complex instruction set computer, and RISC reduced instruction set computer in the CS type. There are a lot of type of instructions. Maybe some of them are rarely used by the programmer. There are a lot of addressing mode for each instruction, and the machine code of each instruction is varied, and some of them needs 1, but some of them needs 2 or 3 or 4 bytes. Of course, writing code in this type of assembly language is easier than the RISC, but in the RISC, most of the instructions perform on registers. In fact, you should read the data from the memory and store it in the registers, and all of the operations should be performed over the data in the registers. Then the results should be stored back in their memory. So there isn't any other thing more like the CISC architecture. One good example of CISC architecture is 80, 86, 80, 200, and 86 and 386, the first generation of the PC computer that are invented by Intel. But the MIPS processor is a RISC structure. So we have a limited number of instructions, and we can read the data from the memory and write it into the memory, so all of the operands should be inside their registers. MIPS is commercialized by Stanford, and it is used in a lot of applications like consumer electronics, network as storage equipment, cameras, printers. Let's see the first instruction of the MIPS arithmetic operations. For example, add and subtract in the mathematics. They have 3 operands. For example, you want to add 2 numbers B and C and store them in variable A. So in high-level language you will write A equal B plus C. In the MIPS assembly language, the instruction for this purpose has 4 parts. The first part is opcode, which tells the assembler what is the meaning of this instruction. Add, subtract, or multiply, divide and/or a lot of other instructions. And these are the parameters that are separated by comma. So one of them is this one is the destination. And there are two sources. B and C are together and stored in A. However, this is not a real assembly. It is only a syntax of the add instruction. As I mentioned, we cannot use variable. Like this in the MIPS assembly language, there should be first bring into the registers and use that register in the instruction. So all of the arithmetic operations in the MIPS assembly language have the same structure or form. There are 1 opcode and 3 operands. The first one is the destination and the second and third one are the sources. During designing the MIPS processor and its language, they follow some design principles. One of them is this one. Simplicity favors regularity. So regularity makes implementation simpler, but the simplicity enables higher performance at lower cost. Let's see one complex example. I assume that the compiler wants to translate this high-level language into the assembly language. F is equal EI plus G should be subtracted from G plus H. The equivalent MIPS code for this one statement in C code includes 3 instructions. First, we should compute each of these processes. For example, G plus H should be add together and store in a temporary variable. And then I should be add together and a store somewhere. And finally we should subtract. As you can see, this is the opcode for subtract as U be the value of the T1 should be subtracted from the T0 and it will store in another location if this is only a general format of the MIPS code. As I mentioned, none of these T0G are accepted in the MIPS code. We should use only registers. You will see it in the next slide. But you want to show that the format of the compiled MIPS code for this one statement in the C code will be something like this. So one statement in high-level language may be translated into several instructions in low-level language. But each of these instructions will be translated to one machine code. There is a one-by-one relation between assembly language and each machine code in a structure. As I mentioned, all of the arithmetic instructions should use the register as their operands. In the MIPS, we have 32 registers and the size of each register is 32-bit. These registers are numbered between 0 to 31. So we have registered 0, register 1, register 2 till register 31. In order to refer to them, we should use a $sign and the number of the register. For example, $3. There are just 3 when you want to use it as one operand. In assembly we call 32-bit data as a word, so the size of each register is one word. Also, in order to make it easier to use the different registers, assembler gives them some name. Temporary registers 0. Register 1 till register 7. There are 8 temporary registers $sign to 027. You can use them in your code or there are some saved variable registers 0 as 1 till 7 and there are other 16 different names that are given to the remaining 16 registers after MIPS. So, you can use both of these symbols in your code. Of course, for programmers it is easier to use the symbolic name T0 T wanted to, for example, instead of using $3, 4, or 5. So for example, register $as 0 as 7's maps onto register 16 to 23 and T0 till T7 are maps onto register 8 to 15. Let's come back to the previous example. Assume that these variables are ripped from the memory and stored in these registers. For example, we have F, G, H, I and J and assume that they are stored in $as 0 as 1 as total $. As 4, the operands are now inside the registers and this is the real MIPS code corresponding to this instruction. First, the value of the $sign is 1 and the last one is 2. These two registers are at together. For example, G and H are in these two registers. We should read them first and then the result will be a store in another temporary registers. In this example, the result is 0. And the other branches is computed by this line, and then these two results will be subtracted from each other's, and the result is stored in another register. Now assume that $10 is corresponding to the if variable. There is a recent instruction to write back the result into the memory. But as you can see inside the arithmetical instruction, we can only use the registers. You cannot use any variable or operands that are in the type of the direct address.